Up to 30 kilovolts, you are primarily measuring the cable's insulation resistance. Between 35 kilovolts and 50 kilovolts, you are likely observing corona discharge. This is a partial discharge that occurs in the air near the conductor surface due to high electric fields. Above 50 kilovolts, the slight increase in current could indicate some minor insulation degradation. However, since the cables passed the test, it is likely not significant. Corona discharge can contribute to the aging of cable insulation over time. It can also generate ozone, which can be harmful to equipment and personnel. Raising the voltage where corona starts can extend the cable's lifespan. Methods to raise corona inception voltage include firstly, increasing cable insulation thickness because thicker insulation reduces electric field strength. Secondly, using a higher quality insulation material because materials with higher dielectric strength can withstand higher electric fields. And thirdly, applying a semiconductor layer to the insulation surface as this layer helps distribute electric field stress more evenly. Testing to 56 kilovolts provides a margin of safety above the operating voltage of 15 kilovolts. It can detect insulation defects that may not be apparent at lower voltages, and it can provide an indication of the cable's ability to withstand short-term overvoltages. I recommend discussing your observations with the cable manufacturer to confirm your interpretation of the results. Also consider increasing the corona inception voltage of the cable if the current at 56 kilovolts is significantly higher than the manufacturer's specifications. And finally, adhere to the recommended guidelines for DC hipot testing in IEE 400 and other relevant standards. When interpreting test results, it is essential to understand the different phenomena that can influence the current readings at various voltage levels. At lower voltages, primarily up to 30 kilovolts in this specific case, the measured current is largely reflective of the cable's insulation resistance. This resistance is a fundamental property of the insulating material and indicates its ability to impede the flow of electrical current. A higher insulation resistance implies better insulation quality and a lower leakage current. As the voltage increases, particularly in the range of 35 kilovolts to 50 kilovolts, corona discharge becomes a more prominent factor. Corona discharge, also known as partial discharge, occurs when the electric field strength around a conductor exceeds the dielectric strength of the surrounding air or insulating material. This can happen at sharp edges, irregularities, or imperfections on the conductor surface or within the insulation. The discharge ionizes the air, creating a faint glow and producing audible noise or radio frequency interference. Corona discharge is an indicator of stress on the insulation and can contribute to its gradual degradation over time. Above 50 kilovolts, a further increase in current may suggest the onset of more significant insulation degradation. However, it's crucial to consider that if the cables have passed the overall test specifications, this increase might not be indicative of a critical issue. It could represent a minor deviation within acceptable limits. Nevertheless, it's essential to investigate and understand the potential causes of this increase to prevent future problems. Corona discharge has several effects on cable insulation and the surrounding environment. Firstly, it leads to the erosion of the insulation material over time, reducing its dielectric strength and lifespan. Secondly, it generates ozone, a highly reactive gas that can damage equipment, corrode materials, and pose health risks to personnel. Thirdly, it can create electromagnetic interference that disrupts nearby electronic devices. To mitigate the effects of corona discharge and extend the cable's lifespan, it's crucial to raise the corona inception voltage. This is the voltage level at which corona discharge begins to occur. Several methods can be employed to achieve this. Increasing the cable insulation thickness is one of the most straightforward approaches. Thicker insulation provides a greater barrier to electrical stress, reducing the electric field strength at the conductor surface. Using a high-quality insulation material with a higher dielectric strength is another effective strategy. These materials can withstand stronger electric fields without breaking down or experiencing corona discharge. Applying a semiconductor layer to the insulation surface helps distribute electric field stress more evenly, preventing localized concentrations that can trigger corona discharge. Testing cables to voltage higher than their operating voltage, such as 56 kV in this case, offers several advantages. Firstly, it provides a margin of safety, ensuring that the cables can withstand short-term overvoltages or surges without failing. Secondly, it can detect insulation defects or weaknesses that may not be apparent at low voltages, allowing for early intervention and preventing potential failures. Thirdly, it provides an indication of the cable's overall health and ability to perform reliably over its intended lifespan. The interpretation of test results should always be done in consultation with the cable manufacturer. They possess the expertise and knowledge to assess the specific characteristics of their cables and provide accurate insights into the meaning of the test data. In addition to consulting with the manufacturer, it's also recommended to adhere to the guidelines and recommendations outlined in relevant industry standards such as IEE 400 and other applicable standards. These standards provide valuable information on best practices for DC hipot testing, including voltage levels, test durations, and acceptance criteria. By following these guidelines, you can ensure that the testing is conducted safely and effectively, and that the results are interpreted correctly. Understanding the nuances of high-voltage cable testing requires a comprehensive approach that combines theoretical knowledge, practical experience, and collaboration with experts. By carefully analyzing the test data, considering the various factors that can influence the results, and seeking guidance from knowledgeable sources, you can gain valuable insights into the health and performance of your high-voltage cables. Furthermore, ensure that all terminations are properly installed and shielded to minimize the risk of corona discharge at the ends of the cables. Pay close attention to the surface condition of the insulation, as any contaminants or irregularities can increase the likelihood of corona. Also take into account the environmental conditions in which the cables are installed, as temperature, humidity, and air pressure can all affect the corona inception voltage. Regular inspections and maintenance can help identify potential issues early on, allowing for timely repairs or replacements. By taking a proactive approach to cable management, you can ensure the long-term reliability and safety of your electrical systems. In the context of the provided information, the electrician's observation of a linear current voltage relationship up to 30 kV, followed by a change in slope around 35 kV and another slight jump between 50 kV and 56 kV, is consistent with the expected behavior of high-voltage cables during DC hipot testing. The linear region up to 30 kV likely reflects the cable's insulation resistance, while the changes in slope at high voltages indicate the onset of corona discharge and potential insulation degradation. However, since the cables pass the test specifications, the observed deviations are likely within acceptable limits. To further refine the interpretation of the test results, it would be beneficial to compare the measured current values with the manufacturer's specifications for the specific cable type and length. This comparison can help determine whether the observed current levels are within the expected range or if they indicate a potential problem. Additionally, it would be helpful to examine the cable terminations closely to ensure that they are properly installed and shielded. Poorly installed or damaged terminations can be a major source of corona discharge and can lead to premature cable failure. Finally, it's important to maintain accurate records of all test results, including the date, time, voltage levels, current readings, and environmental conditions. These records can be used to track the performance of the cables over time and identify any trends or anomalies that may warrant further investigation. In addition to the factors mentioned above, it's also important to consider the type of insulation used in the cables. Different insulation materials have different dielectric strengths and are susceptible to different types of degradation. For example, cross-linked polyethylene, XLPE, is a commonly used insulation material for high-voltage cables, known for its good electrical properties and resistance to moisture. However, XLPE insulation can be susceptible to degradation from exposure to ultraviolet, UV, radiation, ozone, and other environmental factors. Other common insulation materials include ethylene propylene rubber, EPR, and paper-insulated lead-covered, PILC, cables. Each type of insulation has its own advantages and disadvantages, and the choice of insulation material should be based on the specific application and environmental conditions. It's also important to consider the age of the cables when interpreting test results. As cables age, their insulation gradually degrades, leading to a decrease in dielectric strength and an increase in leakage current. The rate of degradation depends on several factors, including the type of insulation, the operating temperature, the voltage stress, and the environmental conditions. Older cables may require more frequent testing and maintenance to ensure their continued reliability. The frequency of testing should be determined based on the cable's age, operating conditions, and the criticality of the application. Cables that are exposed to harsh environments or that are used in critical applications may require more frequent testing than cables that are installed in protected environments or that are used in less critical applications. It's also important to have a well-defined maintenance plan in place to address any issues that are identified during testing or inspection. This plan should include procedures for repairing or replacing damaged cables, as well as measures to prevent future failures. By taking a proactive approach to cable management, you can ensure the long-term reliability and safety of your electrical systems. Remember that the interpretation of high-voltage cable test results is a complex process that requires a combination of technical knowledge, practical experience, and careful attention to detail. By following the recommendations outlined in this discussion and consulting with experts when needed, you can gain valuable insights into the health and performance of your high-voltage cables and ensure the safety and reliability of your electrical systems. The type of test being performed also influences the interpretation of the results. A DC hipot test applies a direct current voltage to the cable and measures the leakage current. This test is primarily used to assess the insulation resistance and identify any defects or weaknesses in the insulation. An AC hipot test applies an alternating current voltage to the cable and measures the leakage current or the breakdown voltage. This test is more sensitive to certain types of defects such as voids or delaminations in the insulation. A partial discharge test detects and measures the small electrical discharges that occur within the insulation. This test is very sensitive to defects and can provide valuable information about the condition of the insulation. The choice of test method depends on the specific objectives of the testing and the type of information that is needed. In some cases, it may be necessary to perform multiple tests to obtain a comprehensive assessment of the cable's condition. It's also important to ensure that the test equipment is properly calibrated and maintained. Improperly calibrated equipment can produce inaccurate results, leading to incorrect conclusions about the cable's condition. The test equipment should be calibrated regularly by a qualified technician and should be used in accordance with the manufacturer's instructions. In addition to the technical aspects of cable testing, it's also important to consider the safety aspects. High voltage testing can be dangerous and should only be performed by qualified personnel who are familiar with the hazards involved. Appropriate safety precautions should be taken to protect personnel from electric shock, arc flash, and other hazards. These precautions may include wearing appropriate personal protective equipment (PPE) such as insulated gloves and clothing, using insulated tools, and establishing a safe work zone. It's also important to follow lockout-tagout procedures to ensure that the cable is de-energized before any testing or maintenance is performed. Always prioritize safety when working with high-voltage equipment. Let's delve deeper into the practical aspects of interpreting DC hipot test results for high-voltage cables. Understanding the factors that influence the current readings and how to differentiate between normal behavior and potential problems is crucial for ensuring the reliability and safety of electrical systems. The initial linear portion of the current voltage curve, typically observed up to 30 kV, primarily reflects the cable's insulation resistance. This resistance is a measure of the insulation's ability to impede the flow of electrical current. The higher the insulation resistance, the lower the leakage current, and the better the insulation quality. Factors that can influence the insulation resistance include the type of insulation material, the temperature, the humidity, and the presence of contaminants. The temperature of the cable can significantly affect the insulation resistance. As the temperature increases, the insulation resistance typically decreases. This is because high temperatures increase the mobility of ions within the insulation, leading to increased leakage current. Humidity can also affect the insulation resistance. Moisture can penetrate the insulation and create conductive paths, reducing the insulation resistance and increasing the leakage current. Contaminants such as dirt, dust, or oil can also accumulate on the surface of the insulation and create conductive paths, leading to reduced insulation resistance. The change in slope around 35 kV often indicates the onset of corona discharge, also known as partial discharge. Corona discharge occurs when the electric field strength around a conductor exceeds the dielectric strength of the surrounding air or insulation. This can happen at sharp edges, irregularities, or imperfections on the conductor surface or within the insulation. The discharge ionizes the air, creating a faint glow and producing audible noise or radio frequency interference. Corona discharge is an indicator of stress on the insulation and can contribute to its gradual degradation over time. The severity of corona discharge depends on several factors, including the voltage level, the geometry of the conductor, the type of insulation, and the presence of contaminants. Sharp edges or irregularities in the conductor surface can concentrate the electric field, leading to increased corona discharge. Contaminants on the insulation surface can also increase the likelihood of corona discharge. The slight jump in current between 50 kV and 56 kV may indicate the onset of more significant insulation degradation. However, it's important to consider that if the cables have passed the overall test specifications, this increase might not be indicative of a critical issue. It could represent a minor deviation within acceptable limits. Nevertheless, it's essential to investigate and understand the potential causes of this increase to prevent future problems. Possible causes of insulation degradation include prolonged exposure to high voltage stress, overheating, moisture penetration, chemical contamination, and mechanical damage. Over time, these factors can weaken the insulation and reduce its dielectric strength, leading to increased leakage current and eventual failure. To determine whether the observed current levels are within acceptable limits, it's essential to compare them with the manufacturer's specifications for the specific cable type and length. The manufacturer typically provides data on the expected leakage current at various voltage levels. If the measured current levels are significantly higher than the manufacturer's specifications, it may indicate a potential problem. It's also important to examine the cable terminations closely to ensure that they are properly installed and shielded. Poorly installed or damaged terminations can be a major source of corona discharge and can lead to premature cable failure. The terminations should be clean, dry, and free from any sharp edges or irregularities. The shielding should be properly grounded to prevent the buildup of voltage stress at the termination points. Furthermore, maintaining accurate records of all test results, including the date, time, voltage levels, current readings, and environmental conditions is important. These records can be used to track the performance of the cables over time and identify any trends or anomalies that may warrant further investigation. The record should be stored in a safe and accessible location and should be readily available for review when needed. When interpreting the test results, it's important to consider the environmental conditions in which the cables are installed. High humidity, high temperature, and the presence of contaminants can all affect the insulation resistance and the likelihood of corona discharge. Cables that are installed in harsh environments may require more frequent testing and maintenance than cables that are installed in protected environments. Finally, remember that the interpretation of high-voltage cable test results is a complex process that requires a combination of technical knowledge, practical experience, and careful attention to detail. By following the recommendations outlined in this discussion and consulting with experts when needed, you can gain valuable insights into the health and performance of your high-voltage cables and ensure the safety and reliability of your electrical systems.